Hello and welcome back to the physics of chemistry. This lecture will focus on oscillations and a particular form of oscillations known as simple harmonic motion. The suggested reading is taken mainly from section 2.2 of the Foundations of Physics for Chemists by Ritchie and Sivia. Just to define an oscillation, so whilst we've encountered forces moving objects from point A to point B frequently, an oscillation is the repetitive variation around a central point. This may occur in situations such as a spring with a mass on the end. If the mass is displaced from this central equilibrium, it will oscillate back and forth. A plucked guitar string, or a pendulum in a clock. So an object in a stable equilibrium is able to move back towards its resting point if it is nudged away from it. So this mass on a spring, for example, is trying to move back to an equilibrium point in the middle. If the strength of the underlying restoring force is proportional to the displacement from equilibrium, then the resultant motion is said to be simple harmonic. This may be a spring connected to a mass, but this may also occur for pendulum motion, and other examples exist as well. If we look at this mass oscillating on a spring a little bit more closely, we can define the equilibrium point. There is a maximum displacement in the top direction from the equilibrium point, and there's also a minimum displacement in the bottom direction, and this mass will oscillate back and forth around this equilibrium point forevermore. If we plot displacement against time, starting from the equilibrium point, the spring is then compressed at the maximum. It extends back out, going through the equilibrium point, to the maximum extension of the spring at this minimum displacement, back to the equilibrium point, and so on. Looking at this displacement versus time graph carefully, you can see that it is a sine wave or a cos wave, depending on where you define it passing through the origin. As it is a wave, we can employ certain definitions. So one of these is the period of the wave, t, which is the time for one complete wave, as time is on the x-axis. We can also define frequency, which is the number of waves per unit time. The relationship between frequency and period is inverse, so frequency equals 1 divided by period. The units of frequency are, of course, hertz, which are the number of waves per second. Another aspect to consider of simple harmonic motion is plotting velocity on the x-axis versus phase space, i.e. position on the y-axis. When this is done, we can see there's 2 points at which velocity is 0, which correspond to the maximum and minimum displacements from the equilibrium position. And the points at which the velocity is at its maximum are either there or there, and that corresponds to when the object is moving through the equilibrium position. This will become important later as we see we can employ concepts from angular motion. Another way of defining the period of a wave for an object undergoing simple harmonic motion is employing omega, which is the angular velocity. This is how quickly the angle is changing of this object. So the period is also defined by 2 pi divided by omega. And as we also know, t is equal to 1 divided by f, omega is equal to 2 pi f. So if you increase the angular velocity, you also increase the frequency of oscillation, which makes sense. Moving on to looking at forces in SHM. So the force is always opposite to the direction of displacement. This means that when the spring is being extended, the displacement x is moving to the right, therefore the force is moving to the left. Similarly, at the bottom, where the spring has been compressed, the displacement is moving to the left, therefore the force is moving to the right. And as you can see, in both cases, the force is acting towards the central equilibrium position. Thinking back to the definition of forces within springs, this force is equal to minus kx. The minus sign indicates that the force is opposite to the direction of displacement, and k is a constant intrinsic to the spring, or as we shall see, other things as well. And finally, to state, as long as the system has no energy loss, the mass will continue to oscillate forever. As we've defined, force is equal to minus k times the displacement, and we also know that force equals mass times acceleration. From these two equations, we're able to define acceleration as being equal to minus k divided by m times the displacement. And whilst the solution to this equation is a little bit too lengthy for this presentation, the solution for x is equal to a sine omega t. This depends upon the starting point, so in this case I've described this as a sine wave. You can also describe it as a cos wave and include a variable depending on exactly where the wave starts. So another possible solution of this is x equals a cos omega t. So you sometimes see both described. Considering this displacement, we can then say velocity is the rate of change of displacement with respect to time. So v is equal to dx divided by dt. Differentiating sine omega t with respect to t, we take the omega out, sine changes to cos, and similarly acceleration is the rate of change of velocity with respect to time, a equals dv by dt. Omega is able to come out of the cos function again, and cos now changes to minus sine. So acceleration is equal to minus a omega squared sine omega t. We also originally defined x as equal to a sine omega t. Substituting x back into this equation, we then arrive at the final equation for acceleration, which is equal to minus omega squared x. Okay, that's all great, but so what? Well, with defining acceleration is equal to minus omega squared x, we can start to observe a couple of things. So a will be at its maximum when x is at the maximum. We've already said x is greatest at either plus or minus the amplitude. So when the spring is at its most compressed or at its most extended. We can also say acceleration is equal to 0 when x is equal to 0. That is when displacement from the equilibrium position is 0. The object is moving through the equilibrium position. Acceleration at this point is equal to 0. We can also examine energy. So going back to springs and the forces and energy that can be stored within springs, energy is equal to half kx squared. Plotting energy versus displacement x. At the equilibrium position, the elastic energy is 0. However, when it's extended out, this energy then increases, or similarly when it's compressed, this energy also increases up to the point of maximum compression or maximum extension. So you can see the maximum elastic energy is at plus or minus A, and we can also see that elastic energy is equal to 0 at the equilibrium position. If we plot energy versus displacement for potential energy, this is the graph we obtain. Similarly, we can examine kinetic energy. So kinetic energy is equal to half mv squared. Again, plotting E versus X. The maximum kinetic energy this time is when the object is moving through the equilibrium position, and then as it extends further out, it will stop moving. At this point, V will be equal to 0. Therefore, there will be no kinetic energy. Similarly, when the spring is fully compressed, it then stops moving. Energy is equal to 0 before it starts extending again back to the equilibrium position. Plotting this, energy versus displacement, we obtain this shaped graph. We can then look at the total energy by combining potential and kinetic, where you can see the shapes of these graphs are both opposite to each other. And this allows us to show that the total energy of the system is constant. It's always cycling between potential and kinetic energy. At the equilibrium position, all of this energy is kinetic. At the limit of displacement, all of this energy is then potential, i.e. elastic energy. With this in mind, we can then discuss undamped v damped oscillations. So within simple harmonic motion, we assume no energy loss to the surroundings. So this oscillation will just continue forever. However, if there is energy loss, then the amplitude of these oscillations will decrease over time until the object reaches a stationary position and has stopped moving. We'll go into this in more details within the seminar itself, but it is worth considering the relevance this may have to chemistry, which will be surprising to you, I hope. So one of the ways in which simple harmonic motion is employed in chemistry is that molecules can actually be viewed as point masses joined together by springs. So instead of viewing these as fixed length bonds, we can actually view these bonds as springs, which are able to then oscillate. Studying molecules, even quite large materials, can actually be viewed as studying a set of simple harmonic oscillators which have been coupled together. The simplest harmonic oscillator in chemistry is a diatomic molecule, and so this can be modelled as two masses connected by a spring of stiffness K. So you have M1, M2, they're bonded together, which we're modelling as a spring, which has a stiffness of K. As we will find out, K will be proportional to a wide variety of things. In some senses, it can be modelled as bond strength, so a spring which is more difficult to compress and extend could be a stronger bond, for example. And we can also say that if one atom is much lighter than the other, the heavy atom is effectively acting as a fixed anchor, and the lighter atom is then executing simple harmonic motion. So in this case, M1 is much greater than M2. M2 is then acting as the object oscillating around a fixed point on this spring, which is the bond between the two masses. And with that, I will finish, and we will discuss these topics in more detail very soon. Thanks.